All right, we're back. So now we're going to talk about the physical implications of what we just learned about the ground states of hydrogen. Okay, so we just understood that the fact that the electron and the proton have spins means that you get four states for the 1,0,0 state, or four basis elements. And the fact that the magnetic moment of the electron and the magnetic moment of the proton interact with each other means that those four states actually get split. The energy levels are that we get two different energy levels. And so you get one energy for the actual ground state, which is the state where the total spin is equal to zero. We learned last time that that state is equal to up, down, minus down, up in terms of the electron spin and the proton spin. And then you get this higher energy for the spin one states, the total spin one states of the electron and the proton. And now we're going to talk about, well, what is that energy and what are the consequences of having this splitting? Okay. So if we want to calculate that energy, then it turns out we could just, so this was the constant that we called C1 in the last video. And so just looking at our results from the last video, we basically had C1 times, what was it, h bar over 4 for that one, and C1 times minus 3h bar over 4 times that one. Okay, and so then the difference is just going to be C1 times h bar, and we can plug in all these constants and just get a number for what that is. Okay, and what is it? It turns out to be delta E equals 5.88 times 10 to the minus 6 electron volts. Okay. So that's really tiny compared to the minus 13.6 electron volts. That's sort of the energy scale for our ground state in the kind of 0th order approximation. Okay, so that's a really, really tiny energy, and you might think, well, that we'll never be able to observe that. It's not going to really make any difference. But it turns out that it is really important in one situation, which is for clouds of atomic hydrogen in outer space, in our galaxy, in other galaxies, and in the space between galaxies. So why is it important? So it's very cold out there, and so in these clouds of atomic hydrogen, there's really not enough energy for many of the electrons to be in anything but the ground state. Okay, so you have all these hydrogen atoms, and pretty much all the electrons are in the ground state. Okay, but they can actually be, there is enough energy, so the interactions with those hydrogen atoms and the background radiation in the universe, this 3 Kelvin background radiation, those photons in that radiation are energetically enough to take an electron that's in the actual ground state and move it up into this triplet state. Okay, and then we can have spontaneous transitions from that triplet state down to the ground state. And so in your clouds, of atomic hydrogen, you have electrons moving up and down between these levels. Okay, and so importantly, so here's our cloud of atomic hydrogen out in the universe, and so here's a hydrogen atom. And so if you have an electron in that hydrogen atom that makes a transition down, then you're going to emit some radiation. You'll emit a photon whose energy is 5.88 times 10 to the minus 6 electron volts. Okay, so what are those photons? If you convert that, so convert to photon wavelength. Okay, so remember, you can first of all use the relationship between energy and frequency for photons. So that's E equals hf. That allows you to find the frequency of the photon with that energy. And then you can use the relation between wavelengths and frequency. Okay, so wavelength times frequency is velocity. So you can calculate the wavelength of these photons. And it turns out that in the end, you find 21 centimeters. Okay, so that corresponds to, that's in the radio wave part of the spectrum. And so basically what that means is that if you have some cloud of atomic hydrogen out there in the galaxy or beyond, then what we expect is actually that there's going to be all this 21 centimeter radio wave radiation coming off of that. And so if we want to make a map of 21 centimeter, or sorry, of atomic hydrogen in our galaxy, then we can just build a radio telescope that is sensitive to this 21 centimeter radiation. And so I wanted to show you a picture of, this is actually a map. Here are the colors, I believe, just represent intensity. So this is a map of our galaxy in 21 centimeter radio waves. And so you can actually, what you're looking at is the distribution of atomic hydrogen in the galaxy. So it's pretty impressive that the reason we can make this picture is because there's this tiny 1 in a million splitting of the energy level of the ground state of hydrogen. And then we get this amazing way to look at the universe, mapping out the atomic hydrogen out there. And here's some cats. Thanks.